This is an explanation of freezing point depression and boiling point elevation and how to calculate the difference in the boiling point or freezing point. So when water is a pure solvent, it freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. We know that when you add a solute to a solvent, it either elevates the boiling point or it depresses the freezing point because those particles get in the way of the normal freezing and boiling process or change in state. So the way that this is calculated is using the equation that you see here first. The change in temperature, or excuse me, the change in the temperature of the freezing point is equal to I times Kf times molality. So Kf is a constant. It's called the molar freezing point depression constant, and it's equal to negative 1.86 degrees Celsius kilograms over moles. I is called the Van't Hoff factor, and we know that the colligative properties are dependent on the number of particles that are dissolved in the solvent. The more particles that are dissolved, the more they can interfere with the freezing or boiling process. And so I stands for the number of dissociated ions or particles. And with a covalent compound, when something like sugar, for example, is dissolved in water, it doesn't ionize into the individual atoms. It just breaks down into individual sugar molecules. So for each mole of sugar, you get 1 mole of sugar molecules that will interfere with the process. With an ionic compound, though, I has to take into account the number of ions that dissociate, because when sodium chloride or magnesium chloride, for example, dissolve in water, those ions are pulled away from the crystal by the water molecules. They dissociate and are solvated. And sodium chloride would dissociate into 1 sodium and 1 chloride for a total of 2 ions per mole of solution. Magnesium chloride is going to dissociate into 1 magnesium ion and 2 chloride ions for a total of 3. So I would be equal to 3 for MgCl2. So the way that this works, let's go ahead and assume that we are trying to find the freezing point when we add 100 grams of magnesium chloride to 100 grams of water. All right, so again, our equation is that the change in the freezing point, or the difference between that freezing point of 0 and the new freezing point, is going to be I times the freezing point constant times the molality. All right, so far we don't have molality, so that's our first order of business. And molality is equal to the moles of solute dissolved in kilograms of solvent. So for this problem, we would have to, looks like it's Z, sorry. First of all, figure out how many moles of solute that we have. So 100 grams of magnesium chloride so 1 mole of magnesium chloride has a mass of 95.21 grams. And if we plug that into the calculator, that gives us 1.05 moles. myself a little more room here. Okay, so that can go into our molality equation up here. 1 point. Let's see, sorry, I keep forgetting to lift up my pen. Here we go. 1.05 moles per kilogram of solvent. So if we go back up here, we said we had 100 grams of water. And so if we change that into kilograms, we have 0.100 kilograms. All right, in other words, the molality is going to be 10.5 moles per kilogram. Okay, so now that we have the molality, we have all the information that we need for the equation. So let me just rewrite that again. The change in the temperature of the freezing point is going to be equal to I times Kf times molality. All right, so if we plug the numbers in, we get 3, because we have 1 magnesium and 2 chlorides, times the constant, which is negative 1.86 degrees Celsius, times kilograms per mole, times the molality. All right. So kilograms cancel, moles cancel, and we're left with degrees Celsius. And plugging that into the calculator, we get negative 58.6 degrees Celsius. Okay, so if we take the original freezing point, which is 0 degrees, and we subtract 58.6 degrees Celsius, we get a new freezing point of negative 58.6 degrees Celsius.